Okay, this video is designed just to be a quick review of the chapter 1 section for the grade 11 functions course, the MCR3U course. So like I said, this is just designed to be a quick review heading into your test for the unit. If you want more detailed explanations of any of the sections, go back and watch some of my previously posted videos on those sections. So the first section you probably covered in the grade 11 functions course was looking at the definition of a function and being able to state the domain and range of a given relation. So most simply put, domain is the values x may take for a relation, or where does the relation exist along the x-axis. In this case, the domain of this relation, it only exists at 1 or to the right. So remember, domain, we're looking at the x-axis. Where does the relation exist along the x-axis? It exists at 1 or to the right, not to the left. So this is how we write it. The domain, I can do a better bracket than that. So we need to do a curvy bracket. The domain, we say x could be any real number given that x is greater than or equal to 1, because the relation only exists at 1 or to the right. It could be any number that's greater than or equal to 1. The range, there are no restrictions on the range for this relation. So I don't need to write any restrictions. Y can be any real number because this relation continues forever this way and this way, so it goes off towards positive infinity and negative infinity along the y-axis. There are no restrictions on the y values for this relation. If we look at, and you'll notice I kept saying the word relation for this and not function. The reason why I said that is because if you were to do your vertical line test to test if this relation is a function, you would see that it fails the vertical line test. Just a reminder, a relation is only a function if there's only one y value that corresponds to a given x value. So that means if I were to drag my vertical line across the relation, does that vertical line ever touch the relation in more than one spot? And you'll notice right away that when x is 2, y could be 2 or negative 2. There are two different y values that correspond to a given x value. So this fails the vertical line test. This is not a function. This, however, this is a function. If we were to do our vertical line test with this relation, it passes the vertical line test. Never is your vertical line touching the relation in more than one spot. So it passes the vertical line test, so this relation is a function. And for this function, the domain, you'll notice the domain, if we look along the x-axis, the function exists everywhere except for, it seems to not want to touch this vertical line here. We call that vertical line a vertical asymptote, and there's a vertical asymptote at x equals 1, because if x was 1, if I plugged in 1 into the equation here for x, the denominator of our function would be 0, and you can't have 0 in the denominator, so that's why there's a vertical asymptote at x equals 1. So for our domain, x could be any real number. You'll notice that it's going to continue forever to the right and forever to the left, so it could be any real number except for, given that x does not equal 1, because there is a vertical asymptote at x equals 1. Also, you should notice that there is a horizontal asymptote going across here. This relation is going to go off forever to positive infinity, off forever to negative infinity, but as it gets closer and closer and closer to y equals 0, it never touches it, but it does keep getting closer and closer to it. It gets closer and closer to y equals 0. It exists everywhere along the y-axis except at y equals 0. So our range, what values could y take for our function? Well, y could be any real number, but y cannot equal 0. And you'll have a horizontal asymptote at 0 whenever the denominator of the equation of your function is a higher degree than the numerator. We have degree 1 in the denominator, degree 0 in the numerator, so we're going to have a horizontal asymptote at y equals 0. Okay, so that's domain and range, and we've clarified how to determine if a relation is a function or not. Next section you would have covered is determining the max or min of a quadratic function. So two methods you probably covered. Method 1, completing the square, which you would have done in grade 10 as well, so I'm not going to explain it too much. But basically the whole goal of completing the square is to get a quadratic that is in standard form, change it into vertex form so that you can easily pull out the vertex of the parabola. It's going to be your HK is your vertex of the parabola. So here's the steps to completing the square. Step 1, you put the first two terms in brackets. And then you leave your C value, your plus 73, off by itself at the end. Next step, whatever is in front of the x squared, you factor it out from what's in the brackets. So I'm left with x squared minus 10x in the brackets. Next step is you create what's called a perfect square trinomial inside the brackets by adding and subtracting half of that 10 squared. So half of 10 is 5. 5 squared is 25. So I need to add and subtract 25 inside the brackets. So I've essentially added 0 in a fancy way because 25 minus 25 is 0. Next, we don't want that minus 25 in there, so I need to get it out by multiplying it by the 3 that is in front of the brackets. So inside the brackets, all I'm left with is x squared minus 10x plus 25. That's my perfect square trinomial. I've multiplied this negative 25 by the 3 to get it out of the bracket, so it becomes a negative 75 outside the brackets. Oh, that 5 kind of looked like a 3 there. So negative 75 plus 73. Last step is we need to factor this quadratics in the brackets. And it's a perfect square trinomial, so it's going to factor nicely. The two numbers that multiply to 25 and add to negative 10 are negative 5 and negative 5. So that would give me x minus 5 times x minus 5, but I'll write that as just x minus 5 squared. Negative 75 plus 73 is negative 2. So my vertex is, my h value is 5, my k value is negative 2. So my vertex is 5, negative 2. And you might also have to state whether it's a max or a min. Since your a value is positive, that means it opens up, which means the vertex is at the bottom of the parabola. So this vertex is a minimum point. Okay, I'm going to show you the other method you might have used as well. The other method you might have used, I'll do it in a different color, is called partial factoring. Partial factoring. So for partial factoring, we have our equation f at x equals 3x squared minus 30x plus 73. What we're going to do for partial factoring, the first step is to set the equation equal to your y-intercept, your c value. Remember, the c value is the y-intercept of the parabola, so I'm going to set it equal to 73. 73 equals 3x squared minus 30x plus 73. And now that we've set it equal to the y-intercept, I'm going to solve it for x. I'm going to solve for what x values have a y-coordinate of 73. Since I know the y-intercept is at 73, I know the x-coordinate of all y-intercepts is 0. One of my solutions is going to be 0, but there's also going to be another solution. And then once I have both solutions, I can average them together. Since parabolas are symmetrical, I can average those two solutions together and figure out the x-coordinate of the vertex, then use the x-coordinate of the vertex to find the y-coordinate of the vertex. So let's just go ahead and solve this, and you'll see how that happens. So first I'll move this 73 over. So I get 73 minus 73 on the left, which equals 0. So 0 equals 3x squared minus 30x. Now solve by factoring. So I'm going to factor out a 3x, so I'm going to common factor this. I can take out a 3x from both of these terms, and then inside the brackets divide both of those by the 3x we took out, and I get x minus 10. And now use the zero product rule to set both of your factors equal to 0. So for this product to be 0, either 3x has to be equal to 0, or x minus 10 has to be 0. And then solve for x in both cases. So x could be 0 divided by 3, which is 0, or x could be 0 plus 10, which is 10. So the parabola has a y-coordinate of 73 in two spots, at 0 and 10. So I know parabolas are symmetrical, so to find the x-coordinate of the vertex, I know the vertex is in the middle of the parabola. All I have to do is average those two x values that I found together. 0, so to average them, just add them, divide by 2, I get 5. To find the y-coordinate of the vertex, all I have to do is plug in that x value of 5 into my original equation of 3x squared minus 30x plus 73. So 3 times 5 squared minus 30 times 5 plus 73. I get 3 times 25, which is 75, minus 150 plus 73. So I get negative 75 plus 73, which is negative 2. And good, I have verified my answer that I got when I was completing the square. I got 5, negative 2 as the vertex once again. And once again, since my a value is positive, I know the parabola opens up, so the vertex is at the bottom, so this is a minimum point. So those are two methods that give you the exact same answer. They both give you the vertex of the parabola. Generally, you'll be able to choose whichever method you would rather when finding the vertex of a parabola. So you can either do partial factoring, or like in red we did up here, completing the square. Both give you the vertex of the parabola. Next, you would have worked with radicals. So in working with radicals, the key skill you're going to need to know how to do is to change radicals into mixed radicals. And to do that, so basically, 4 root 3, that's a mixed radical. It has a coefficient and a radical being multiplied together. That's a mixed radical. I can change this into a mixed radical if there are any perfect square factors of 27. So perfect square numbers are like all the numbers squared. So like 1 squared is 1, 2 squared is 4, 3 squared is 9. So 1, 4, 9, 16, 25, 36, those are all perfect square numbers. So are there any perfect square numbers that divide evenly into 27? Yeah, 9 divides evenly into it. So I can break up root 27 into root 9 times root 3 because 9 times 3 is 27. The reason why I'm doing that is because on the next line, when I simplify this, square root of 9 is 3. So I can rewrite this just as 3 root 3. I'm going to do the rest now as well. I can't simplify 4 root 3 because there are no perfect square numbers other than 1 that divides evenly into 3. I can simplify root 243. 81 is a perfect square number, and that divides evenly into 243. 81 goes into 243 3 times, so I can break it up into root 81 times root 3. And this one here, minus 8 times root 81, well, square root of 81, 81 in itself is a perfect square number, and 81 is equal to 9 squared, so the square root of 81 is 9, so this is just minus 8 times 9 plus 2. And now I'll continue my simplification down below here. I've already simplified my first term to 3 root 3, minus 4 root 3, plus the square root of 81 is 9, so I can write that as 9 root 3, minus 8 times 9 is 72, plus 2. And now I can collect my like radical terms together. So, since all three of my first terms all have the exact same radical part of the expression, I can collect them together by just adding and subtracting the coefficients. So I have a 3 root 3 minus 4 root 3 plus 9 root 3. So 3 minus 4 is negative 1, plus 9 is 8, so that gives me 8 root 3. The radicand does not change when adding or subtracting. The radicand is the number under the square root. And then negative 72 plus 2 is negative 70. That's my simplified expression of what we had at the beginning. Next, there's some multiplication involved in this next one. So we have distributive property. What's inside the brackets has to be multiplied by what's outside the brackets, so distribute what's outside to both terms on the inside. Now when multiplying, the radicand is going to change. You're going to multiply the radicands together. So I have negative 3 root 3 times root 3. These radicands, the numbers under the square root, have to be multiplied together. So that gives me negative 3, and then root 3 times root 3 is root 9, because 3 times 3 is 9. Next, negative 3 root 3 times 5 root 2. The coefficients get multiplied together, so negative 3 times 5 is negative 15. And then the radicands get multiplied together. 3 times 2 is 6, so that gives me root 6. And then I can simplify root 9. The square root of 9 is 3. And I can't simplify root 6. There are no perfect square numbers other than 1 that divides evenly into 6. So all I'm left with is negative 9 minus 15 root 6. And that's it for radicals. The next section you probably covered was solving quadratics. So there's two ways you can solve quadratics. If a quadratic is factorable, you could solve it by factoring. And I'm going to go over the shortcut I would have showed you in this section earlier. So the shortcut, and notice this quadratic, the a value is not 1. I chose a quadratic where the a value is not 1 because that's generally where students struggle, is factoring quadratics where a is not 1. But if you remember this shortcut, it's not too bad. So we want to find two numbers that have a product of 5 times negative 4. So a product of negative 20 and a sum of negative 19. The two numbers that satisfy that product and sum are negative 20 and 1. Now, with these two numbers, they both have to be written as a fraction with the denominator of whatever a value is. The a value is 5, so write negative 20 over 5, write 1 over 5. Then simplify both of those fractions down below or beside, whatever you find easiest. So proc negative 20, sum of negative 19. This fraction will simplify, negative 20 over 5, that'll simplify to, 5 goes into both of them, it simplifies to negative 4 over 1, and 1 over 5 does not simplify. Now these two fractions are going to give you all of the numbers you need in your factors. So this one is going to give us the numbers we need for our first factor, this one is going to give us the numbers we need for our second factor. The denominator is the coefficient of the x, the numerator is what's added to the x. So our first factor is just 1x minus 4, I'll write it as x minus 4, and my next factor is 5x plus 1. And it's been factored. If you want to check and make sure it's factored properly, you could FOIL it out and make sure you get back to our original expression here. But now that it's factored, we can solve easily. Using the zero product rule, just set both of your factors equal to 0, and then solve for x. So my first x-intercept is at 0 plus 4, which is 4. My second x-intercept is equal to negative 1 over 5. I got that by moving the plus 1 over, got negative 1, then divided to 5. So my x-intercepts are at 4, 0, and negative 1 over 5, or negative 0.2, comma 0. Those are my two x-intercepts. And another thing I should point out, notice that the quadratic was set equal to 0. Whenever you're solving, make sure your quadratic is set equal to 0, because to find x-intercepts, I should have mentioned that as well. Solving means finding the x-intercepts, or sometimes you'll see them called roots of a quadratic. The reason why we're setting the quadratic equal to 0 is because the y coordinate of any x-intercept is 0, because the point is going to be right on the x-axis. The y coordinate of any point on the x-axis is 0. That's why the quadratic is set equal to 0 before solving. Then we're solving for what x values make the quadratic have a value of 0. And that'll tell us the x-intercepts, 4 and negative 1 over 5. You could also solve using the quadratic formula. Quadratic formula, x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Now, first thing you have to do, set your quadratic to 0 before solving. Negative 3x squared plus 4x plus 2. So whenever you're solving using quadratic formula, make sure you're in standard form first. Make sure you're in the form ax squared plus bx plus c, and we are. Here's our a, here's our b, here's our c. All we have to do is plug those into our quadratic formula and simplify. And make sure you know, in grade 11, we always leave our answers as exact roots. You don't evaluate and then round your answer and get approximate roots. Always leave as exact roots. So you have to use the skills you learned working with radicals to do that. So let's plug everything into the quadratic formula. So we have x equals negative b, so negative 4 plus or minus the square root of b squared, so 4 squared minus 4 times a times c, all over 2a. Now let's simplify the radicand, the number or everything under the square root. We call that the discriminant as well. You hear that called the discriminant. And make sure you know when you're solving a quadratic, you have three possibilities. You could get 0, 1, or 2 solutions depending on what you get under the square root. If under the square root is negative, if the discriminant is negative, you'll get no solutions. If this equals 0, well, adding 0 and minusing 0 is the same thing. You'll only get one unique solution. If under the square root is a positive number, you will get 2 unique solutions. So let's see what we get in this case. Plus or minus, we have 4 squared is 16, negative 4 times negative 3 times 2 is 24, so we have 16 plus 24, which is 40. And this is over negative 6. Now, in grade 10, you probably would have typed this in on your calculator now, your two cases, and then got 2 answers and rounded your answers. But this year, we're going to leave it as an exact answer, but we can simplify that root 40. We can write that as a mixed radical, because there is a perfect square number that divides evenly into 40. 4 is a perfect square number that divides evenly into 40. So I can break up root 40 into root 4 times root 10. Root 4 times root 10. But the square root of 4, I know what that is. That's 2, so I'm going to rewrite that as 2 root 10. Plus or minus 2 root 10 over negative 6. Now when I have a negative in the denominator, I'm going to want to try and cancel that out by, I'm going to factor out a negative from the top. I'm actually going to factor out a negative 2 because 2 goes into 4 and 2. So I'm going to factor out a negative 2. Then in brackets, divide both of my terms here by the negative 2 I took out, which would give me 2. And then when I divide by a negative, it's going to make that plus a minus and that minus a plus. So it's just going to switch them. Minus or plus root 10 all over negative 6. And then I can simplify negative 2 over negative 6 goes to 1 over 3. And my final simplified answer is going to be x equals 2 minus or plus root 10 over 3. And then if you want, you can break it up into your two possible answers. It could be 2 minus root 10 over 3, or it could be 2 plus root 10 over 3. And those are our two possible answers for this quadratic here. Okay, let's move on to the next section. Sorry. The last section you would have covered in this chapter probably is linear quadratic systems. So it's a linear quadratic system. Most simply put, it's a line, a parabola, and a line. And if you're solving a linear quadratic system, you're figuring out where do they intersect. Now they could intersect at two spots like that. You could have two solutions. If there's two solutions, then the line is called a secant to the parabola. You could get one solution where it just touches the parabola at one spot, and then the line would be called a tangent to the parabola. Or the line can never intersect the parabola, and you get zero solutions. And this should be familiar, right? When we talked about solutions to a quadratic, you could get 0, 1, or 2, because when we solve the linear system, the linear quadratic system, we're essentially going to be solving a quadratic equation, and you could get 0, 1, or 2 solutions depending on whether your discriminant is negative, equal to 0, or positive. Okay, let's go ahead and solve this. So the steps to solving a linear quadratic system is you have to first figure out, okay, we're going to figure out where do they intersect, if they intersect at all. To do that, you have to set the equations equal to each other. So set 4x squared minus 15x plus 20 equal to 5x minus 4. You set this equal to that. I've set the equations equal to each other. Now you solve what values of x make the quadratics equal to each other. So that means what are the values of x at their points of intersection, if their points of intersection exist. So then we have to solve this. Now we talked about solving before. When solving, you have to set the quadratic equal to 0. So I'm going to bring everything to the left. Bring the 5x to the left, becomes a minus 5x. Bring the minus 4 over, becomes a plus 4. The right side is now empty, it's equal to 0. Now I'm going to collect my like terms, and then I'm going to solve. We could solve using quadratic formula, or we could solve by factoring in this case. Factoring is going to be quicker this time. I'm going to common factor first. Whenever you can common factor first. So take out a 4, because 4 is a common factor for all three terms here. Minus 5x plus 6. Then just divide that 4 to the other side, and it's gone. 0 divided by 4 is 0. So I have x squared minus 5x plus 6 is 0. And then solve by factoring. If we set up our cross, I need two numbers of a product of 6, sum of negative 5. Those two numbers are negative 2 and negative 3. Put the negative 2 and negative 3 over whatever your a value is. In this case, it's 1. Remember, the denominator is the coefficient of x, and then add whatever the numerator is. So my first factor is 1x minus 2. I'll write that just as x minus 2. My second factor is 1x minus 3, which is just x minus 3. And once again, you should always just do a quick check, FOIL this out in your mind, and make sure you get back to this quadratic here. Then if we want to finish solving, set both of your factors equal to 0, and then solve each of the equations. So x could be 2, x could be 3. That means there's 2 points of intersection. They intersect when x is 2 and when x is 3. But I want the coordinates of both of those points. So I need the y coordinate that goes along with those x coordinates. So I now have to, so that was my first x value. This was my second x value. So if I'm going to find my points of intersection, there's going to be 2 of them. My first point of intersection, POI number 1, I'll figure out what's the y coordinate when x is 2. Now I could plug 2 back into either of my original equations to get the y-coordinate. It'll be the same no matter which one we plug it into, but I'm going to use the linear one because it's going to be easier. So 5x minus 4. So g at 2 equals 5 times 2 minus 4. G at 2 equals 10 minus 4, which is 6. So that means my first point of intersection is 2, 6. My second point of intersection, I know they also intersect when x is 3. So solve g at 3. G at 3 equals 5 times 3 minus 4. G at 3 equals 15 minus 4, which is 11. So my second point of intersection, 3, 11. Now the last type of question you would have solved, that I did with my class for this chapter anyway, was figuring out, given the slope of a line, find what value of k, so find the value of the y-intercept that would make the line tangent to a given parabola. Tangent means one point of intersection. For that to be true, the discriminant of a quadratic, to get one answer, the discriminant of a quadratic has to be equal to 0. So what we're going to do is we are going to start solving the same way we did the last question, set the equations equal to each other. 3x squared plus 4x minus 1 equals negative 2x plus k. Now set it equal to 0, because when we're solving we have to set it equal to 0. Bring the negative 2x over, becomes a plus 2x. Bring the plus k over, becomes a negative k. It's now equal to 0. Collect our like terms, plus 6x minus 1 minus k equals 0. Now, I have two variables here, so I can't solve this equation, but I could figure out, I know if the line's going to be tangent to the parabola, when solving this, I would have to get the discriminant equal to 0. If I was using the quadratic formula to solve, the discriminant would have to be 0 if I'm going to get one solution. So if I'm going to use the quadratic formula and check the discriminant, remember the discriminant is b squared minus 4ac, the part under the square root. The discriminant has to be 0. So keep in mind, if this is my parabola, this is a, this is b, and this whole part is my constant term, that's my c. If I plug those into here, I can solve for what value of k would make the discriminant equal to 0. So let's do that. b is 6, so 6 squared minus 4 times a is 3 times c is negative 1 minus k. I now have an equation with one variable. I can solve for that. 36 minus 12 times negative 1 minus k. Distribute that negative 12 into the brackets. 36 plus 12 plus 12k equals 0. 48 equals negative 12k. Divide the negative 12, I get negative 4 equals k. And that would be my final answer. If k was negative 4, if this was a negative 4, if I were to solve this linear quadratic system, I would get one solution, meaning that the line, I'll draw with a negative slope since we have a negative slope, the line would intersect the parabola only at one spot. Okay, and I think that's it for the chapter. So like I said, that was just a quick review. We did it in under 30 minutes. That was my goal, so it's under 30 minutes. That's all of chapter 1 in 30 minutes. If you want a more detailed explanation of any of those sections, so if you got confused during any of those, any of the examples I did, go back and watch the video on that section. And then go to jensenmath.ca and download the entire review and practice it on your own.